good afternoon, ladies and gentlemen. A warm welcome to you here in the blauwe zaal of Eindhoven University of Technology. And as rector of the university, it's my pleasure to present our academic awards of 2012 for the work, of course, that has been done last year in 2011. This year's award ceremony is part of the first Dutch Technology Week. We all know about the Dutch Design Week. In fact, the Dutch Design Week is a major event in the Netherlands in the area of design that attracts a lot of attention. And the Dutch Technology Week is a showcase of the technological innovations that originate here in the region of Eindhoven. And the Dutch Technology Week too is attracting a lot of attention. Last Sunday, about 5,000 parents and children visited the campus for the TU experience. A fantastic success, and today, as part of the Dutch Technology Week, the academic awards put the spotlight on our bright young researchers and students who will help maintain the outstanding level of innovation, of science and of technology in this region. The nominees and their projects show that the TU Eindhoven really contributes to the solution of major societal challenges in the areas of energy, health and smart mobility. And many of the research projects have been conducted in collaboration with parties outside of the university. The close links between science, industry and government here in the Brainport region Eindhoven prove their value yet again. I'm proud that our university produces so many promising young people, engineers, technological designers and PhD candidates every year. And this year's academic awards highlight the best final project, that is the best master thesis, the best design report and the best doctoral thesis completed at our university in the year 2011. I would like to start with the nominees for the TUA Final Project Award, and I invite all the nominees to come forward. And that's quite a lot. Okay, very visible in this way. Yeah. There is a cross, cross on the floor, so when I mention your name, you and I will go to the cross and then Bart can take a picture. Okay? For later. Okay. Ladies and gentlemen, every year each department nominates the best thesis in one of its master programs for the TUE Final Project Award. And I'm going to give each of you a certificate in recognition of you being nominated by your department, because that, ladies and gentlemen, by itself is an outstanding achievement. Okay, and I just explained the procedure with the cross. So I will start with Timothy Ellis from Applied Physics. Applied Physics. Next one is Angela van der Heijden from the Built Environment. Is Angela here? Yes, she is. There was a question mark. Bart Sprong from Biomedical Engineering. Bart. Bart Sprong. Thomas Franken from Chemical Engineering and Chemistry. Thomas. Maaike van het Westeinde from Electrical Engineering. Maaike. Janine Kierkels from Industrial Design. Dat moet jij zijn, dat kan niet. Martijn Jaspers from Industrial Engineering and Innovation Sciences. Martijn. Right. Nu hebben we Joep Evers from Mathematics and Computer Science. Joep. Joep Evers. Jelle Hellings, again Mathematics and Computer Science. So one is mathematics, the other one is computer science. You are? Computer science. Okay, so the last one is Maarten Belen from Mechanical Engineering. All right. First of all, ladies and gentlemen, the jury wishes to express that all final projects, all these master theses were really top quality. But still the jury had to come to a decision on the final winning project. So the question is, who of you will be the winner? Ladies and gentlemen, after long hours with pizza and beer, after serious debates and delicate discussions, the jury came to a unanimous decision and conclusion. That is to say, with all noses in the same direction. It is with much pleasure, ladies and gentlemen, and with further ado, the winning thesis of the TU Eindhoven Final Project Award 2012 is Modeling Crowd Dynamics, a multi-scale measure theoretical approach by Joep Evers from the Department of Mathematics and Computer Science. Okay, so may I invite you to take your seats back again and okay, thank you. Okay. And it's up to you to explain. Oh nee, ik moet het eerst nog doen. Sorry. Sorry.
Ja, oké, maar ga maar.
Okay, hang on. I do this only once a year, so every time I forget what the order is. Anyway, so the laudatio. The collective motion of individuals, for instance, flock of birds or human crowds, is a fascinating phenomenon. Joep Evers has used a recently developed two-scale modeling approach to take into account the individual driving forces at the microscopic, the small scale, and external forces exerted on groups at the macroscopic, the large scale. He then extended this model with elements borrowed from the theory of mixtures in fluid mechanics. With this innovative approach, Joep surprised the jury in a very positive way. In his well-written thesis, he presents model-based simulations of the behavior of pedestrians moving opposite directions in a narrow hallway. Joep, congratulations with this award. The idea was that now the other nominees would return to their seats, but they are already there. And can I ask you to give a brief presentation on your work?
Imagine that it was not just us in this room, but say 5,000 people, and that all of them wanted to get out at the same moment. Or even worse, imagine that you were in the situation on the picture on the right. Do you know what happened there? I will tell you. This ended in tragedy. This is the Love Parade event in Germany, Duisburg, 2010. And here 21 people got crushed in the crowd. 21 people because there was only one tunnel, which was the entrance to the festival train. And in the same time, this tunnel was also the exit of the festival terrain. I was shocked by this event, but ironically, this was exactly the moment where I had to decide what the topic would be of my master's project. And I wanted to understand what went wrong on that day. And I wanted to prevent this from happening ever again. But before we can solve the big problem, we need to understand the small bits that make up the whole. And this brings me to the scope of what my project turned out to be. We start with the very simple rules according to which we believe that individuals move in a crowd. This is at the micro level. And we want to understand how from these rules, these simple rules, the large-scale behavior of the crowd emerges. And in order to understand this is exactly the point where the fascinating field of mathematics comes into play. Now don't be afraid, because this is actually the only formula that I will show you today. But I do want to show this, because this is actually the crucial point of my model. This is the simple rule according to which I believe that people decide how they want to move. What I show you is the velocity of a single person. This is the speed and the direction. And I believe that in principle, every individual has its desired velocity. This is the velocity that it would have if no other people were around. So imagine that I'm faster than you and I want to be first at the reception after this ceremony. Then no other people are around and I can walk according to my desired velocity. But unfortunately, or maybe also fortunately, we are many people today, and this is why I need to adapt my desired velocity with respect to the contributions of every individual. So what we see here is I have a desired velocity and I have contributions from the people in my environment. I need to adapt my desired velocity according to all of these contributions. So now I show you the simple rules on the micro scale. And now let's see what happens at the large scale if we use this simple rule. Now I show you a corridor with two groups of people. So imagine it could be the tunnel in Duisburg. And now we have a quite moderate number of people there. And what we see is that there is a nice form of self-organization. These people turn out to move in lanes. And in these lanes, they follow people moving in the same direction. And what the result is that the flow is nice. People can walk through at a quite nice pace and the pace they want to move. But if we now switch to the next slide, and I increase the number of people in the corridor, then we see all kinds of nice patterns, which are nice for mathematicians to study. But the crucial point here is that the flow fully stagnates. The people don't flow through anymore. And you can imagine, and Duisburg teaches us, what happens if we let more and more and more people enter here. Now I have a model which is able to show me when the flow stagnates. But we are far from really preventing accidents. So this project is actually a starting point for my PhD project. And I'm happy that I'm now in a PhD project within the graduate program of the ICMS Institute, in which I can continue my research. And now there is only one more message I want to get across today. We cannot bring back those people that died in Duisburg, but we can use mathematics to make these events safer in the future. Thank you.
Heel mooi. Mathematics is going to save the world, ladies and gentlemen, which is very good. Okay, next we continue with the TU Eindhoven Design Project Award 2012, and again I invite all the nominees to come forward. The TUE Design Project Award goes to the best design project from one of the technological designer programs of the Stan Akkermans Institute here in Eindhoven. And as in the case of the master students, I'm going to give each of you a certificate in recognition of you being the best of your class, the best of your designer program in 2011. Right. First one on the list is Kris Zych from the Design and Technology Implementation Program. Kris. Next one is Yongyang Kai from Logistics Management Systems. Fernando Polanco from the that's Chemical Engineering, Process and Product Design program. Lorraine Liang from software technology, that's computer science. Yes. And then the last one is Rafal Kochilnik from User System Interaction. Okay. Okay, and maybe you noticed it, ladies and gentlemen, but all are from non-Dutch. Eh? So very good that they came to Eindhoven for these programs. Again, ladies and gentlemen, the jury was very much impressed by the quality of the projects. But again, the jury had to make a choice. Ladies and gentlemen, again, after long hours with pizza and beer, after serious debates and delicate discussions, the jury came to a unanimous conclusion decision. That is to say, with all noses in the same direction. With much pleasure, ladies and gentlemen, and without further ado, the winner of the TUE Design Project Award 2000 and 2012 is Kris Zych of the Design and Technology Instrumentation Program for his design radio frequency density meter. Kris, congratulations. Now we do it in the correct order, okay? Kris has done his design project at IHC Merwede, the market leader in the development and manufacturing of dredging equipment. So we go from crowd dynamics, we go to dredging equipment. For dredging, two parameters are crucial for the production. One is the slurry density and the other is the flow velocity. It is common practice in industry to measure these parameters with a radioactive emitter-transmitter system. But Kris developed a radio frequency RF system that is easier to transport and that doesn't require highly qualified personnel. Hence, it is much more cost-effective. The system has a high accuracy, it is robust and ready for tests on board of a real cutter dredger. The jury characterizes Kris's work as a beautiful combination of theory and practice. Very analytically, he breaks up a complex problem into smaller, manageable pieces. Kris, congratulations with this award. Okay. So, may I then invite you to return to your seats and give you a short explanation about your project.
Ladies and gentlemen, I'm honored and pleased to have the opportunity to stand here in front of you and tell you a few words about my adventure which I experienced at IHC Systems, adventure with the dredging business. So first I need to explain you what is dredging, what is the mysterious word. It's essentially picking up sand from a seabed. For example, this ship is a giant vacuum cleaner. He lowers the suction tube onto the seabed, starts to trailing it, sucks in a mixture of water and sand, puts it into a hopper on board, transports it to the shore, and then unloads it. Here we see a process of unloading sand. Looks very spectacular, costs a lot of money. That's why it must be very efficient. And the dredge master, the guy who takes control of the ship during this action, he's focused on only one parameter, which is the density. Density of the mixture flowing in that pipe. So there is a very great need for a continuous measurement of the density. There is a device for that, a solution known for years now, but it's very inconvenient. It uses strong radioactive sources. So at IHC Systems, a new concept was developed which uses radio waves to detect the density. So it's as follows. We take a steel pipe and we fit it with two antennas on the opposite sides. One antenna transmits the radio wave, second one receives it. And the received signal will directly depend on what is between those pipes. In other words, what is the density. So, but at this point, you should ask me, wait a minute, you want to suck in seawater. And there is radio waves cannot be transmitted through seawater. We all saw the movie Hunt for Red October, right? So, yes, it's true. It's a challenge. We expect that the signal will be highly attenuated, and the signal-to-noise ratio can be a problem, which can be overcome by the sufficient input power. So, everybody were enthusiastic. The device was built. This is how the prototype looks like. This white panel covers the antenna. You can also see how the old-fashioned method looks like. This orange casing holds the radioactive source. We hook it up with the custom-made electronics, and this device was placed on a ship to make real dredging, real test. And it didn't work. There's some bigger problem regarding salty water than initially anticipated. And this is precisely the moment when my adventure starts. I joined the group to investigate the problem and mainly to make it work. So we had 1 year of time, one goal, and not really a clue how to get there. So we decided the best way to examine the problem is to go back on the ship. But this time we'll do it in a more convenient way. We built a ship in-house. This is the pump test setup we created, and we placed our prototype in it. So we have a big pump here, circuit which circulates the water and sand mixture constantly. So, and on top of it, by the way, it's about 5 meters high. On top of it, there's an opening when I can stand and add kitchen salt. That's why I can simulate the seawater. So we are 3 months before the project deadline when the setup is ready. And the most difficult part and the most extruding part of the measurement start. During the day, it's sand, sweat, and tears. During the night, it's looking at the results. And we're waiting for with this attitude, we can expect a breakthrough. 16 tons of sand later, two floods, and one major malfunction of the pump, we got it. What was happening? I told you we're transmitting a signal to the transmitter antenna. Here it's presented in the frequency domain, and we expect the same signal at the other side, but attenuated, so the peak will be much smaller. So imagine my surprise when I saw this. First question, what is this second peak? That was simple to trace. It's created at the transmitter side. It's just non-linear effect. It's a third harmonic. But even so, we expect that this harmonic will be gone at the receiver side. It will be totally attenuated. The reality was the other way around. To really understand what happened, we had to change the way of thinking about our system. We had to apply the waveguide theory. In other words, our pipe is a waveguide, and it acts like a high-pass filter. High-pass filter which corner frequency is shifting depending on the salinity of the water. And that's why it's simpler for the higher frequencies to pass the mixture rather than the low frequency. And this very high third harmonic at the receiver side was misleading our readout electronics. Since we understood what happened, it was easy to find a solution. We just placed a low-pass filter before the transmitter antenna. The high-frequency component was gone, and from this moment, the device works smoothly, exactly as it was predicted. So, to wrap up, we gained, after the end of the project, we gained the understanding of the system. And we achieved a radio wave transmission through the seawater in the configuration which was to date nowhere reported in the literature. To add to that, we understood what is the influence of salty water onto the operation of the device. Now we can predict how the signal will look like in different dredging locations depending on salinity. Which means IHC Systems has a technology to offer the device which doesn't have a radioactive source and is an innovative method of measuring density. This is also my personal benefit because I was hired by the company and my job is to design, develop and design the commercially available device. So we expect to have launch by the end of this year. Again, I was given 1 year, one goal, and now this time I have a head full of ideas. So the predictions are good for the future. So I thank you, the committee, for this award, for this honor. But personally, I need to thank people who stand behind me in this project. Herman, Ward, Martijn. Without you, I wouldn't be standing here right now. Thank you for it. Thank you very much.
Well, first of all, thank you, Kris, for your presentation, and thank you very much, Raoul Liu of Quadrivium, for your excellent performance. Ladies and gentlemen, some of our students win awards and some make music. I think this was really excellent. We conclude with number 3. These are the Doctoral Awards, with the TUE Doctoral Project Award 2012 for the best dissertation, the best PhD thesis. And I would like again to invite the nominees to come forward so that I can present them with a certificate as well. Welcome. I hope we have everybody. It's a long list. We start, this is alphabetic, no, this is not alphabetic order. Okay, anyway, we start with Joep Beckers from Applied Physics. Jos. Applied Physics. Gijs Dingemans, also from Applied Physics, but he is absent. He is in Texas, in Austin, Texas at the moment, on a conference on solar cells. Very good. Ineke Wijnheimer, also from Applied Physics. Ineke. Ineke. Anke de Vries, Biomedical Engineering. Yes. Let me see. Yes, Jovan Jovanovic from Chemical Engineering and Chemistry. The envelope, ladies and gentlemen, the envelope contains money. The envelope is very important. You should not lose it. Mohammed Al-Fiyad from Electrical Engineering. And he is also not here?
In the States.
He's in the States because he found a job in the United States, so that's very good. Daniel Cavallo from Electrical Engineering. Daniel Cavallo. Bart Gijssen from Electrical Engineering. Yes, Milan Marel, Electrical Engineering. That was Electrical Engineering. Bart Hengeveld, Industrial Design. Okay, Bart, Industrial Design. Marieke van den Toren, Industrial Engineering and Innovation Sciences. Niels Willems, Mathematics and Computer Science. Niels. And the last one is from Mechanical Engineering, Thijs Donkers. And you should realize, ladies and gentlemen, that these nominees, these candidates, are selected from about 200 PhD candidates each year, so it's quite a selection. In this case too, ladies and gentlemen, the jury was impressed by the quality of the theses that were nominated by the various departments. But also this jury had to make a decision. Ladies and gentlemen, after long hours with pizza and beer, after serious debate and delicate discussion, the jury came to a unanimous conclusion. That is to say, with all the noses in the same direction. The winning thesis of the TUE Doctoral Project Award 2012 is Dust Particle Diagnostics in Plasmas by Joep Beckers from the Department of Applied Physics. Joep, go ahead. Ladies and gentlemen, let me tell you why, okay? The thesis of Joep Beckers concerns so-called dusty plasmas. God, so now we have plasmas, crowd dynamics and what is it, dredging. Complex plasmas containing dust particles. These are present in various plasma processes in the semiconductor and in the solar cell industry. His research followed two directions. The formation of dust particles in plasmas, that's one thing, and the use of those dust particles to diagnose the plasmas itself, the other thing. In an interesting twist, Joep challenged gravity for his experiments. He did this by placing a plasma reactor in a centrifuge to get higher gravity, and also on an Airbus 300 in parabolic flight for zero gravity. Joep has developed very elegant models to explain his experimental data, by which he was able to unravel properties of plasmas that up to now could not be studied directly. The jury was impressed by the fine combination of innovative experiments with analytic modeling, something we like to see, modeling and experiments. And an additional strong point is that Joep Beckers succeeded in describing his research in a way that is appealing also to the non-specialist in the field. Joep, congratulations with this award. Okay, a brief explanation, please, Joep.
Well, it already was a great honor to be nominated for this award, but it's even unbelievable to win it as well. So I'm very enthusiastic to tell you today a little bit about my research of the last years. I would like to do that with the help of a painting by my brother Bas Beckers. And he did what was almost impossible. He catch in one picture all the key aspects of my research. So what you see in the middle is a dust particle in a plasma, which is interacting with a laser beam, and which is observed by the eye of the experimentalist, and basically my eye. Why this washing machine and this almost crashing airplane is there, this will become clear to you later, I hope. So in my dissertation, three subjects were of importance. First of all, a plasma. You see here a plasma operated above an electrode. And what makes this plasma so special is that it can generate light. So for that purpose, a plasma is used widely as street lighting and the TL bulbs in your home. But what is even more interesting is when a plasma touches a wall, then you see here that you get a certain space region in which there's no light generated. And in this region there are very high electric fields present, and these fields have a lot of applications in, for instance, solar cells and the semiconductor industry. What we did is we also put dust particles in this plasma, and by that the dust particles are charged and they fall to the bottom, and they are actually trapped in this space charge region. So they are trapped in the electric field of the sheet. Well, we have here a picture of our plasma, and what we see is indeed that if you put dust particles in a plasma and you illuminate those particles and you make a picture of them, that they're indeed all trapped in one plane. And the reason why is because gravity is pulling it down, and an electric force generated by the electric field is pulling the particles up. Well, if you now have knowledge about the charge on these particles, and from our analytical model we have that, we can estimate the electric field at this specific position, so at the position of the dust particle. Well, of course we are not interested at the electric field at one position, but throughout the whole plasma. And since we cannot change the electric force here without changing the plasma, we need to change gravity. And that's easier said than done, but let's zoom out to the painting again, to the washing machine. We all have such a device at home, and what we know is if we spin the washing machine, our laundry is accelerated outwards and there comes an extra force on our laundry. Well, we started thinking and we thought, why not replacing the laundry by our dust particles? Well, we did that, but we didn't have a washing machine in our laboratory, so we did the following. We made a plasma vessel with a plasma in it. We injected dust particles, illuminated them by a laser beam, and made a picture with a good camera to track their position. And then we placed the whole thing in a centrifuge, which was developed. And when we are spinning this thing around at full speed, we have 50 kilometers an hour. Imagine that you have 100 kilograms at the end, then this will end up to be 10 times as heavy as normal on Earth. So we are spinning around 1,000 kilograms with 50 kilometers an hour here. So we didn't place that fence for fun, but just for safety. So the first results, we indeed see that if we increase the gravity, the dust particles go down, and we can do the trick at different positions. That was the easiest part of our research, increasing the gravity. For decreasing the gravity, we had a different trick, and we participated in a parabolic flight campaign in Bordeaux in May 2011. And what you basically do then, you build your experiment in an Airbus A300. And this describes a parabolic trajectory. That means that the pilot pulls up, and during that phase you have 1.5 times the normal gravity. And when it has an angle of 47 degrees with the horizon, it switches off its engines and the airplane comes into a free fall. And so also everything and everybody inside the airplane is in free fall, and we could do our experiments with that. So I here have a movie. You see here the niece of my master student, Dirk Trinicus. I see him there sitting there. And the reason why you see his niece is because we were advised to lay down during the pull-up phase, because you have then 1.5 times gravity, and if you move your head like this, then your equilibrium organ can be influenced. And basically, at some people it does. 1 out of 10 people get ill during the flight. And we had one crew member in our team who also got ill, and I can assure you it's not pleasant, and the pilot doesn't go back for getting you back to the airport. You see here indeed that we are in the 0 G phase, so everybody is floating. And we had to optimize our experiment, because if you're flying away you cannot operate at all. So also Dirk is liking this. Well, besides these experiments are very fun to do and very exciting, we got a very good result out of them. What you see here is the proof that, first of all, we can measure the electric field in the plasma sheet without disturbing the plasma. That's very important because normally you stick something in to measure it and that disturbs it. But even more important, you see here the kink in this electric field. And that means that we force our dust particle into another region of the plasma. It's called the plasma presheet, and that was developed in 1930 by physicists who couldn't match the mathematical equations in the boundary of the plasma and the plasma itself. So we are now the first ones since 80 years to prove that this theory actually is right. So with that, I would like to end my talk, but not before thanking this university and the group Elementary Processes and Gas Discharges of Professor Kris Zych. He personally supervised me, and I think together we went to great heights, not only in the airplane, but also in unraveling the plasma sheet. Then I would like to thank ESA and ESRON for supporting us financially to do these experiments, and Novus Pas for organizing the parabolic flights. And I want to thank my current employer, Ushio Extreme Technologies, for giving me the possibility to again look at a very exotic plasma. We are developing their extreme UV sources for the lithography. And last but not least, I would like to thank all my family-in-law, all my friends, and of course Miriam. Thank you all.
Very exciting story, ladies and gentlemen. Zero gravity, parabolic Airbus, unbelievable. I don't know how it is with you, ladies and gentlemen, but hearing these three winners, I mean, and also if you look at the material of the nominees, it makes me very proud because the quality of the people is really, really excellent. Ladies and gentlemen, on behalf of the board of the university, I would like to invite you to join us for a reception. That reception will take place in the main building over there, through that door. There you can learn more about the different projects, the work of and the research and design project of the nominees and the winners, because there is an exhibition on the first floor of that building. And a brief description of the project is also published in a brochure, and that will be handed out when you leave this lecture room. And I would like to invite the winners to join me over here for the traditional photo with the rector. And I would like to thank you, ladies and gentlemen, for being present here this afternoon, for supporting the candidates. I think that's really important to them. And I thank you for your attention. Thank you.